Okay, thank you. First of all, thanks to Dr. Shankar Raman and my PhD guide, Professor Vijayan, for inviting me for this talk. I'm really honored. And of course, thank you everyone for joining for this session. Okay, so today we'll be covering a bit of details on exciton-polaritons and some background physics on polaritons. So the aim of this talk is to give some introduction on exciton-polaritons. It's not going to be an exhaustive talk in the sense that I'm not going to, give you a lot of charts or plots or a lot of advanced physics based on polaritons. Because if you are interested after this talk, you can always go back and have a look at what is actually happening in today's polariton research community. So the idea of today's talk is to try to inspire you to pursue a research or read more about polaritons. So that's the main idea. So sometimes it will be a tutorial mode. In the beginning of the first few slides are going to be a tutorial mode, and then I'll be discussing the physics behind these polaritons. And then I'll be introducing the different types of systems where we can achieve exciton polaritons. And then we'll be moving slowly into the kind of research that I have done during my PhD on exciton polaritons in a special type of artificial material called metal organic framework. So, and then I will give you some details on my material and how we can achieve polaritons. And then I'll be explaining on the experimental aspect of it. I mean, how to experimentally see polaritons, how to experimentally verify that polaritons are present in our system or not. So those things I'll be covering. So it's going to be not very difficult to understand, I hope. And then finally, I'll be giving you some recent applications on polaritons. So yeah, let's begin. So photons and excitons. So those are the two characters of our today's talk. So let's begin with a photon. So we know what is a photon. I don't need to tell anything about a photon. All of us know what is a photon. So in fact, there are two types of photons in the sense that there's a free space photon, which are freely moving in space. Basically, these photons are not confined. But I'm not interested in those types of photons. I mean, the free space photons. I'm kind of interested in confined photons, especially in a cavity, in an optical cavity. It's because confined photons are really useful. We can make use of confined photons. Free photons, of course, they are useful for communications and all that. But there are many other applications for confined photons, and we are going to see all of them today, at least some of them today. So when I say confined photons, I mean these photons can be confined in any sort of cavity. It need not to be the fabric-porous cavity which you are currently seeing. So you can see that a photon, we have already described what is a photon. And yeah, so we were talking about the confined photons. So confined photons are the photons that are confined in a optical cavity. It could be a fabric-porous cavity, just like what you are looking at. So we have two mirrors here, blue color. Okay, let me take the laser pointer again. So two mirrors, and then light can come inside. I mean, come into this cavity from one side and get trapped inside this cavity into different modes. Because if you speak of a cavity, then it means only certain energy levels can be sustained within the cavity, because energy modes are quantized inside the cavity. So it need not to be a fabric-porous cavity always, although we are going to discuss more about fabric-porous cavities today. It could be any type of cavities. It could be a photonic cavity. It could be a dielectric cavity, or it could be a ring cavity or a disk cavity. It could be anything. As long as these photons are confined, we are okay with it. I mean, we can have exciton polaritons. if we have confined photons. So we are interested in confined photons. So the first recipe for realizing an exciton polariton is to get a confined optical mode or confined photon in an optical cavity mode. Now, let me talk about an exciton. So again, we all know what an exciton is. An exciton is an electron-hole pair, which again can be seen in different types of materials, perovskites, 2D materials, organic materials, and even in different types of atoms, we can see all these excitons. So these excitons, being a pair of electron-hole pair, are entirely different. I mean, they possess an entirely different properties compared to a single or a bare electron or a bare hole. When they come together and when they act as a single entity, they express different properties and they give an entirely exotic properties to the material where they are living. So we are interested in those materials where excitons can be seen. If excitons are not present, we will do something to create them first, and then we will manipulate these excitons inside the material. So there are two different types of excitons, Van Helmont excitons and Frenkel excitons. So Van Helmont excitons are the excitons which are usually seen in inorganic semiconductor materials. And these are of small binding energy, meaning binding energy in the order of, let's say, 10 milli EVs. These are very small. So these are actually less than the room temperature. Therefore, these are not very stable at room temperature because energy can be given into such excitons so that excitons can be, these electrons can escape from this Coulomb attraction from the hole. So these are really unstable, especially at room temperature. So usually we see Van Helmont excitons at low temperature, at cryogenic temperature. And their radius is very large because the Coulomb interaction is very weak. So they usually have a large radius, but they always, go as a pair, like a couple. Now we have another set of excitons called Frenkel excitons, which are usually seen in organic materials, like, for example, dyes, rhodamine dye or rhodamine B dye. So there are different dyes that we are familiar with. These Frenkel excitons are nothing but the excited state of a dye. If I have a rhodamine B molecule, which is at the ground state, it doesn't have any Frenkel exciton. Now, if I give a correct amount or right amount of energy into or photon into this molecule will go into the first excited state or the singlet state. I mean, there are different states. First excited state. And then we can say that this molecule has a Frenkel exciton. So that is how it is defined, Frenkel excitons. And these are really stable even at room temperature. It is because their binding energy is in the order of EVs. We can have 1 EV binding energy excitons, Frenkel excitons. And because binding energy is very high, it has a very small radius. They are like very close to each other. So they love each other. So they are very close to each other. So basically, these are very strong. So we will look into both type of excitons and see whether polaritons or exciton-polaritons can be formed under these two different types of excitons. Now, let me tell you what is an exciton-polariton. Now we have already covered the confined photons and their discrete energy levels, and the excitons, two different types of excitons. So what are exciton-polaritons? So for the tutorial purpose, let me take just one single exciton. It could be any exciton, doesn't matter which type it is. And then I'm taking a Fabry-Perot mode with a few longitudinal modes, as you can see here. This is the first mode, this is the second mode. So I have just given you just two different modes. Now, in order to form an exciton-polariton in a cavity or in a system or a polariton system, there are different names. What you all need to do is you take the exciton material, the material where you have this exciton, and then just put it inside a cavity. In this case, it's a Fabry-Perot cavity. So this is how it looks when you do that. So you can see that these are the two mirrors of the cavity. The two blue lines are the mirrors, mirror 1 and mirror 2. And this red, this curve represents the first longitudinal mode. And this yellow sheet, small thin layer of this exciton material, represents the material that is going to provide the excitons to form exciton-polaritons. So basically, what are these polaritons or exciton-polaritons? Usually, we think in terms of either energy, or let's say photons, or in terms of matter, right? So either photons or material or matter. But exciton-polaritons are a special type of hybrid particles, meaning these particles possess the characteristics of both a photon and a material particle. It could be an exciton in this case. So it's a kind of, like double-phased particle. Sometimes it acts like a material particle, or sometimes it acts like a photon. So depending on like different situations or different scenario, this can act like a photon or an exciton. So this possesses like two different phases, the material phase as well as the energy phase, I mean the photon phase. So that's why these particles are called half light, half matter particles. These are not actually half, because sometimes it can be 75% light and 25% matter. So, but usually people say that half light, half matter particles for this, for some reason. Yeah. So in this case, again, coming back to the scenario of how to form this exciton-polaritons, the condition, the necessary condition for a system to satisfy, to create or to form exciton-polaritons is to have something called strong coupling. So strong coupling means it's a kind of interaction between the photon. So in this case, the photons that are coming from the first mode and the exciton. So basically, once I put such a simple, the polariton system, what happens is that the exciton from this layer will start to interact with the photons in the first longitudinal mode. So basically, it's an interaction, and this interaction can happen at at different varying degrees or different strength. Sometimes the interaction is weak interaction, sometimes it is strong interaction, and sometimes it is ultra strong interaction, or sometimes the interaction is like very high, even more than ultra strong interaction. So depending on what regime of interaction you are in, you can get different physics out of this single system. So that is a real idea that's a real magic of this. So if you have weak interaction, then there is nothing going on, which we will see why, because there is no interaction, right? Photon will remain as a photon and exciton will remain as an exciton. So these are like two independent systems there. So there is no combined effect here. But as soon as it goes into the strong coupling regime, so there are certain conditions to be satisfied for that. But when those conditions are satisfied, then we get exciton-polaritons. So in this case, I have put a thin layer of MOS2. So it could be a series of layers, maybe different quantum wells or gallium arsenide. So there are different materials that we can use for providing these excitons. So the idea is that we need strong coupling. That is a necessary condition. Strong coupling between exciton and photon. Now let me introduce a small parameter called in-plane wave vector here, or you can call it as parallel wave vector. So what happens is that once these polaritons are formed inside this cavity, these polaritons cannot stay within the cavity forever, right? Because every cavity has some leaky effect. So after some time, these polaritons are going to lose the energy and then emit some photons corresponding to the energy of the exciton-polariton. And this energy, which is coming out of this exciton-polariton, can move at different directions. It can move, maybe completely vertical to this cavity or at a certain angle. So we can actually, get some sort of spectrometer and then place it out of this cavity and then collect all the light that is coming out of this cavity. So these light or these photons basically has all the information about the polaritons, because these photons are basically coming from the polaritons. So that is how we characterize the exciton-polaritons. Now, in order to do such a measurement, we need some parameters called, in-plane wave vector, out-of-plane wave vector, and in-plane wave vector is what is going to be very important, because this also represents the angle of emission of the exciton-polariton, because in-plane wave vector, as you know, it is proportional to the sine of the emission angle. So for small angles, you can sometimes consider this plane wave vector as proportional to the angle of emission. So those are the details which we will see later. So basically, parallel wave vector is the wave vector of the light that is coming out of this cavity at a certain angle, let's say. So this is just one of the components of the wave vector. Okay, so summarizing all this, these are basically quasi-particles. And experimentally, you can get the information, or you can even check whether exciton polaritons are existing inside your system from something called band diagram, or fancy name EK diagram, energy wave vector diagram. So experimentally, what you all need to do is to get somehow an energy wave vector diagram, and then see whether you see any anti-crossing behavior at the exciton-photon resonance. We'll see what that is here. So now, how to identify exciton-polaritons in a system? So on the left-hand side, you can see a graph, and on the right-hand side, you can see a horizontal line. So left-hand side tells you the dispersion diagram of a cavity photonic mode. Okay, it could be nth cavity mode, doesn't matter. It's always going to be quadratic. So it has a quadratic nature. And the important thing is that on the x-axis, the wave vector is the in-plane wave vector, which I have just mentioned before. Now, on the right-hand side, we have this dispersion diagram of the exciton. So exciton, it doesn't change with the direction or the in-plane wave vector. So its energy is always going to stay constant. But for the photon, it's going to be different depending on the in-plane wave vector. Now, these are the two different energy band diagrams independently, but our aim is to see what could be, or what would be the energy band diagram in a strong coupling system. So if I have such a cavity, just like before, we had this Fabry-Perot cavity and the thin sheet of exciton inside it. So this is how we get the EK diagram if there is no polariton. If there is no strong coupling, we will get two independent dispersion diagrams, one corresponding to the exciton and another corresponding to the bare cavity mode. But now this is where the things are going to change. If there is a strong coupling, then instead of two independent band curves, we get another two different curvatures. As you can see here, as indicated as the upper branch, which is the red dotted line above the exciton line, and this is called the lower branch, which is below the exciton line. So if there is an exciton polariton in your system, in that case, what you can see is you see a splitting of the energy band at the resonance. So you can see that at resonance, there is no crossing. We have an anti-crossing, meaning the crossing is avoided somehow because of the strong coupling. So this is called the anti-crossing at the resonance. So this is a bit bigger picture. And the difference between the upper branch and the lower branch at resonance is called the Rabi splitting. So Rabi splitting is usually used in the quantum region. And definitely, of course, this is again related to quantum. So Rabi splitting is a energy, which is a parameter that tells you how strongly your system is coupled. I mean, you have photon and exciton. So what is the strength of interaction between these two? So if the Rabi splitting is large, if the coupling is very large, then you will have a upper branch somewhere here and lower branch somewhere here, where the energy difference between these branches it's very high. So meaning you have a strong, very strong coupling system. And if there is no coupling, then you will see something like this. So there is no anti-crossing, only crossing. So again, coming back to the different, as I said, these two are upper branch and lower branch. Now you might ask, okay, so where are the particles? Where is the photon? Where is exciton, right? Now exciton and photon, they have somehow combined and formed a new particle. Now what happened to this exciton and the photon? So there is no certain or specific answer to that question. You can only answer this question based on the wave vector of the polariton. For instance, we have two particles now, two polariton particles that came from the one photon and one exciton. One particle is in the upper branch and another particle is in the lower branch. And was that a question or? Okay, yeah. So if you consider the lower branch here, depending on the wave vector, for the zero wave vector, you have this polariton behaving like a photon. So this polariton has like more it behaves like a photon more than an exciton. It has 50% of exciton and the 50% of photon at the resonance. So at these 2 points. And again, if you come here, the polaritons with this certain wave vector has more exciton-like character. So depending on which wave vector you are in, and depending on what type of branch you are in, because if you go to the upper branch, it is just the opposite. So towards the bottleneck, you have this photon-like character. So it is both exciton and a photon. Again, it depends on the wave vector. Now, let me quantify the coupling, the light matter coupling strength. So Rabi splitting is, as you can see here, there's a small equation here. This Rabi splitting is proportional to some constants, some parameters here. So N corresponds to number of excitons that are simultaneously coupled to the cavity mode. And Q corresponds to the quality factor of your cavity, because you can have different types of cavity. You can have DBR cavities or a simple, a glass piece, a glass slab itself can act as a cavity with a very, very low quality factor. So when the quality factor reduces, the Rabi splitting reduces, meaning the chances of getting these polaritons are again reduced a lot. And this V corresponds to the mode volume, meaning how small your the electric field within the cavity is confined. So that is the mode volume of the electric field. So lower the mode volume, the higher the coupling strength. And again, for the strong coupling to happen, you need to have this Rabi splitting higher than the sum of the two different leaky factors. The first one is the cavity leaky, cavity rate constant, leak rate constant, or the decay rate. And this is the exciton decay rate, because exciton cannot stay as an exciton forever. It has a decay rate. And then photons that are from the longitudinal mode will again start to lose or leak through the cavity after some time. So that has a decay rate. So the Rabi splitting should be greater than the sum of these two. Otherwise, there is no strong coupling. Now we know how to increase the strong coupling. You can either increase N or increase Q or reduce V. So that is how you rationally design different types of systems to achieve Rabi splitting. So usually we do not get anything by accident. We design it. So these are some of the polariton systems. These are some of the typical polariton systems. The people have achieved 2D, polaritons in 2D perovskates, where they have a top reflector, just like the system that we have just discussed. And then we have a gain medium. Gain medium in the sense, it's the medium that provides the excitons. And they have also demonstrated lacing from this, which we will discuss in detail in the coming slides. And you can see that this is upper polariton branch and this is lower polariton branch. So I have only given you the half of only the first quadrant of this graph. And there is another systems like zinc oxide nanowires. Nanowire can act as a cavity. So its end facets can act as two mirrors. with with a refractive index contrast. So this can act as a cavity. And then we have perovskites, cubides, and WSE2 Rydberg states. So all these systems are typical polariton systems, but there are many other different varieties of polariton systems, even liquids, even with biological molecules like the green fluorescent protein, people have achieved polaritons. So one of the main, the usual strategy to design a polariton cavity is to get a cavity, yes, and to get an exciton active material. And the common trend is to use a DBR or a metal cavity or an inorganic or a biological material as a exciton provider. But the problem with this normal approach is that fabrication of a high Q factor cavity requires a very complicated lithographic processes, which many researchers or many people can't afford, or it's very difficult basically. And also, if you are going with the Vanier mode excitons, you can only realize them in cryogenic temperatures. So that is again going to confine or restrict or the research scope, because when it comes to the room temperature, these are unstable. So this is where my research comes. We have sort of overcome most of the limitations of this common approach by introducing a new type of artificial material called metal organic framework, or in short, MOF. So MOFs are not actually used for realizing polaritons. The chemistry, people use this MOF for gas storage, gas absorption, and for catalysis, and some nonlinear optics. So they use MOF generally for all these things. So for physicists, MOFs are not of that interest. But then when we worked at our lab, we found that we can also have sustained exciton polaritons in such structures. So basically, what is a MOF? A MOF is like a polymer. So it has a repeating unit which will repeat itself into all the three directions to form an entire structure. And this basic unit cell contains an organic linker and some metal ion. And sometimes it has a lot of voids inside, as you can see here. So within these voids, other people usually put some sort of molecules as a guest. So this entire MOF will act as an entirely, it will show some different properties in the presence of such guest molecules. So basically, it's an organic or coordination polymer. So in our lab, we had a collaboration with IIT Kanpur, and Dr. Mayank from IIT Kanpur, he made such a very nice MOF micro plates. These are micro single crystals, which are basically red in color. And these are very different from the normal MOF systems in the sense that he has incorporated a dye molecule, which is called which is a very rhodamin B dye, which is a well-studied dye molecule. But usually people use these dye molecules inside the porous structure of the MOF as a guest molecule. That is how people usually, that's a common approach. But what he has done differently is that he has used this rhodamin B dye as one of the ligands of the MOF structure, and he has used metal. So basically what he got was a stack of 2D layers. All these, so you can see a schematic of such a crystal. You can see that there are several layers of rhodamin B layers molecules, and every layer is connected to each other or kind of bonded to each other through pi stacking of these dye molecules. And these are very strong stacking so that they cannot slide. So these are like very rigid, solid structures. And since we use a dye molecule, which is an organic molecule, we can leverage the presence of fungal excitons. Because as we know, fungal excitons are very stable at room temperature. So it can be used to create, exciton-polaritons if possible. But then if you look at the structure, the physical structure of this molecule, it more or less looks like a cube or a rectangular slab with two faces which are opposing to each other and parallel to each other. So this is similar to a cavity, like a fabric cavity. This inherently, each single crystal of this morph microplate inherently is a fabric cavity, because we have a refractive index contrast across this boundary here and here. So because of this refractive index contrast, these two facets can act as a mirror. Not a very good fabric cavity, because the quality factor is going to be very low. It's in the order of tens or hundreds, but that is enough. The reason why it is enough is because in order to get strong coupling, we had an equation before. We just need to get large number of molecules coupled to a cavity mode at the same time. So we had a factor called n, if you remember. So since each layer, in this figure we have just, I don't know, maybe 50 layers, but in reality there are thousands of layers in a single crystal. So there are thousands or I don't know, like maybe millions of molecules available for the formation of polaritons. So the Rabi splitting can be very high, although the quality factor pulls down the Rabi splitting. The value of n, since it is very large, it dominates. So that is why we got polaritons in our system. So this is just the formation of these polaritons. So we have the dimerization happens in the Frankel excitons first, which are just details which are not really related to the formation of polaritons. So if you are interested, we can come back to this slide later. Now we know that in our microplates we can have polaritons. Now how to measure it? So it is very simple. We just need to get the EK diagram. And how to get an EK diagram? The straightforward way to get an EK diagram, band diagram, is to do the angle resolved reflectivity measurements. Why it is angle resolved reflectivity measurements? Because as I said, if you take the band diagram, the x-axis of the band diagram is a in-plane wave vector, which is proportional to the angle. So practically, the parameter that is accessible for an experimentalist is to get the angle or the emission angle. So we will create a band diagram. Instead of in-plane momentum, we will directly put the angle. That's it. There are at least two methods to do this. The first method is what you can see here. I'm not going to the details of how to do the measurement, but because this is kind of obsolete now, there is another method which is what people commonly use these days. It's called Fourier imaging, which is again a well-established method. So Fourier imaging or Fourier spectral imaging is a method where you basically image the Fourier plane of a lens into a 2D camera, or a 2D camera in the sense like a 2D sensor. So along the one axis, you get the energy information. Along another axis, you get the angle information. So as long as we can have some prisms to disperse the light that enters into the spectrometer, then we can have this band diagram directly from the sample. So this is very simple. We have the sample here. Then we put an objective lens here because samples are so small, micrometer size. And what we do is we shine white light through this objective lens. Then we collect the reflected light. And then we find out where the Fourier plane is, usually which is inside the barrel of this objective lens. Then we simply, using two different lenses, we take this Fourier plane and image it on the slit of this spectrometer. Then the rest will be taken care. So these are some of the results from my experiments. So you can see a few, red color images. So if you look at the figure A, there are two colors, red and black. So red color indicates the polariton branches, which is fitted with green curves. So these polariton branches are fitted with polariton coupled oscillator Hamiltonian. And this blue line corresponds to the exciton, and this yellow curve corresponds to the bare cavity mode. So we cannot see blue or yellow curve. These are fitted theoretically. We can only experimentally observe the polariton branches like the red curves here, which are fitted with the green curves. It's because polaritons are always present. So as soon as you shine some light to probe the polaritons, we get it. Now, if you take another, if you go to the figure B, where the crystal thickness is 8.5 micrometer, which is greater than the 4.1 micrometer thickness of the figure A. As the thickness of the cavity increases, as you already know that, there will be different, or there will be many photonic modes that can simultaneously sustain. So each of these photonic modes are going to separately couple with the exciton that is present, meaning the Frankel exciton. So depending on which photon couples, we get different polariton branches, not just upper or lower. We get many upper branches and we get many lower branches. Now, for instance, if you look at the largest crystal thickness, if you look at the figure C, you know that there are P1, P2, P3, P4, all are the different labels for polariton branches. So as the thickness increases, the Rabi splitting decreases. That is what is we have seen here in the figure D. And we have last year we have published a paper in Advanced Materials where we studied in depth of what is actually happening, why Rabi splitting reduces with thickness. So if you're interested, you can always look into it. Then we have, again, from the experiments, we have verified that the polariton condition is satisfied. We have got the reflectivity data, and then the Rabi splitting is greater than the other two leaky factors. So we finally confirmed that these are indeed polaritons, strong coupling. So now this slide is not actually my work. This is from one of the works from NTU, Singapore. So I put this slide because I felt that this is really important. We have been only discussing about the reflectivity measurements. Now this is about the photoluminescence behavior of exciton-polaritons in a system. So the first figure here basically indicates that as you increase the pump power. Okay, so let me give you a brief background of about this work. So what they did was they took a nanowire, perovskite nanowire, and then they shined a certain laser onto the nanowire, and then they increased the power of this laser. Then they collected the photoluminescence from this nanowire. So that is what you see in the figure A. So as they increase the pump, which is the laser pump intensity, they finally at a certain intensity, they called it as the threshold pump, which is the transition from the polariton PL, usual PL, which is all these, it looks like noisy data, but it's not actually noisy. It's in the log scale. That's why it looks like noisy. And then what happens is that as long as you enter a certain threshold pump laser power, the spectrum will start to lace. And that lacing is what you see here. Again, if you increase the pump power beyond the threshold power, you will start to see a peak arising around the 2.9 EVs. And correspondingly, this is how the full width at half maximum, which is the blue color. So after the PTH, the full width at half maximum suddenly drops, because now this full width at half maximum represents the full width at half maximum of the lacing mode. Here it represents the FWHM of the broad PL. That is why it is very large. And then again, the peak power increases after the threshold. And then if this is actually a lacing or a polariton lacing or a normal lacing, how do we distinguish it? So we distinguish it using or looking at the blue shift. So as the pump power increases, if there is a blue shift to the peak, in this case, the peak is around 2.9. If there is no blue shift, then there is no sort of interaction between the polariton reservoir. It is just could be some other reason for this sort of lacing. But if there is a blue shift in the peak, then we know that there is some sort of different sort of particles. It could be polaritons. It could be the polariton reservoir interaction. And then this blue shift is very high up to the threshold, which is around at 10 microjoule per centimeter square. And after that, the blue shift is very small. I mean, the change in blue shift is not very significant, although we increase the pump power significantly. So these are well studied theoretically. So the first reason for this large stop is because of the polariton reservoir interaction. Because we have a lot of polaritons and we have a lot of excitons. When I say reservoir, I mean just excitons that are not converted into polaritons. So we have interactions between them. But then after threshold, most of these are converted into polaritons, and they undergo a certain phase transition called Bose-Einstein condensation. And then we have a lot of polaritons, and these polaritons interact to each other. But therefore, the blue shift is not very significant as before. So those are the details. So these are all the experimental aspect of polaritons. And now let me go to the final session, which is applications of polaritons.
Sir, 5 more minutes.
Okay, yes. The first application is the inversionless lasing. Usually, these are all the lasers we know: distributed feedback laser, Fabry-Perot laser, and vertical cavity surface emitting lasers. But all these lasers, they need something called population inversion. So we need to pump the material hard enough such that all these ground state molecules or ground state atoms or molecules or whatever will be depleted and then populated at a different excited state with a sort of population inversion. And then we need a stimulated emission for normal lasing. So the condition for lasing, as we know, is the existence of population inversion. So we need to, pump the material so hard. But the disadvantage of such an approach is that pumping a material very hard means you have to give a lot of input energy, so that this input energy will be somehow converted into coherent stream of photons called lasers. So we are having a lot of energy expense already. So this is where the importance of inversionless lasers come in. In this case, we don't need to satisfy the population inversion criteria. Instead, we can have laser-like light without undergoing the population inversion mechanism. So this is how it is. So if you look at this polariton typical band diagram, all these green dots are the polaritons formed at the bottleneck. Let's say when you hit the material with a some sort of pump laser first, very low energy, microjoules per centimeter square. Then if you increase this pump energy, there will be again more and more polaritons will be formed here. Then they will start to collide each other within a small confined spatial region. And then after a certain pump threshold, what happens is that all these polaritons will suddenly, quickly, spontaneously come into a certain state where the energy is constant. In this case, it is 2.2 eV, and the wave vector is 0, and they are all in phase. All these polaritons are in phase. Initially, they were in different phase, but after the pump threshold, it undergoes a spontaneous transition into a condensate, in the form of a condensate. So these polaritons at this point in the EK diagram are called Bose-Einstein condensate. These are still polaritons, but they have energy. So if they emit, it's going to be monochromatic. They are all in phase. So when they emit, they are all in coherence. All photons are going to be incoherent. And since the wave vector is 0, meaning if it emits, it's going to emit at a single direction. It's going to be highly directional. So whatever the light that comes from this sort of system is going to mimic a normal laser. And there is no way that we know, right, whether it is coming from a population inversion method or from an inversionless method. So in this case, there is no population inversion happened, only the transition happened. So these are Bose-Einstein condensation, and the decay of this Bose-Einstein condensation results in lacing-like effect. So these are called polariton lasers. So these are new types of lasers. And the important advantage is that compared to the normal lasers, we don't need much energy to excite this condensate. So we can still operate all these. It's very power efficient. We can operate it microjoules per centimeter square. And another very important and very recent and upcoming application is the quantum computing with condensates. All these condensate polaritons can have two states, either phase or polarization, so they can act like qubit. So these qubits can be used for quantum computing and neuromorphic computing and for quantum blockade. So there are many exotic applications that people are trying to realize using these polaritons and polariton condensates. So this is a very recent hot field with a lot of change happening on a daily basis. Okay, so I think that's the end of the talk. Yeah, thank you. I think I'm